Hello and welcome back. In this lecture, we are going to look at a C++ implementation of merge sort, and we are also going to analyze its performance. Here is a quick recap of some of the relevant topics we have already studied. We have looked at the sorting problem in general. Specifically, we have looked at two sorting techniques, selection sort and merge sort. And for merge sort, in the last lecture, we looked at the intuition behind merge sort. We saw that it was basically a divide and conquer strategy, and the key step in merge sort is that of merging two sorted subarrays into one larger sorted array. In this lecture, we are going to look at a C++ implementation of merge sort, and we are also going to analyze its performance. Specifically, we will count the number of basic steps that are needed to sort an array of size n by merge sort. So let's quickly recall the basic idea behind merge sort. We are given an array which is unsorted and contains a certain number of integers. We first divide this into two subproblems of almost the same size. So if the original size was n, each of these two sizes is roughly n by 2. Then we solve each of these two subproblems. Basically, we sort the first half of the array and the second half of the array separately. And after I have sorted them separately, I take these two sorted subarrays and I merge them together into one larger sorted array that contains all the elements of the original array. So what were the key steps involved in merge sort? We basically divided an array of size n into two subarrays of roughly n by 2 size, and of course if n is odd, then these two subarrays will not be exactly the same size, but their sizes may differ by 1, and this was an easy step. Then we recursively sorted each subarray of size n by 2 using the same technique as the one that we used for sorting the original array, and the terminal case of this recursion was arrays of size 1. In these cases, the arrays are already sorted, so we do not need to recurse anymore. And we also saw how to merge sorted subarrays each of size n by 2, and if you recall from the last lecture, we saw that this merging of sorted subarrays can actually be done quite efficiently by making a single pass over each sorted subarray. So how might a C++ implementation of merge sort look like? Here is what a program might look like. So we have the main function in which I have used an integer array A of size 100. So I am going to be able to read at most 100 integers. Then I ask the user to give the count of integers that she wants to sort. I read in that number and then I do some input validation. Basically I check whether the number of integers that the user has given us to sort is less than or equal to 0 or greater than 100. If so, we print an appropriate error message and return -1. Note that if the main function had executed as expected, I would have returned 0. Here there was an unexpected execution because of invalid input, so I returned -1. So the caller of the main function, which is the operating system in this case, can figure out from this returned value whether something unexpected happened or not inside the function main. Now after I have read and validated the inputs, I am basically going to ask the user to give all the integers to sort, and I am going to read them in a simple for loop, and I am going to read them in the array A. So note that the elements are now going to be stored in A0 through AN-1. After I have read the elements, I am going to call merge sort, pass the array A to it, and say that the starting index for the elements to be sorted is 0 and there are a total of n elements. So basically I want to sort the elements A0 through AN-1, and after that we could have some other code which does something as yet unspecified with this sorted array, and finally we return 0. Now what does the function merge sort look like? Here is how it might look like. So let us first look at its precondition and postcondition. As a precondition, I require that the starting index in the array should be less than the ending index, and both must be within the array bounds of A. As a postcondition, we are going to guarantee that the part of A between the indices start and n-1 will be sorted, and in this particular case, since we are interested in sorting in decreasing order, so this will be sorted in decreasing order. Note that I have passed an integer array as a parameter here, and if you recall from our lecture on selection sort, when I pass an integer array, basically inside this function, whenever I refer to the array A, I am really referring to the same array that the main function used when it called merge sort. This is not copy by value, this is not call by value anymore. So what do I do inside the function merge sort? The first thing I do is to check for the termination case of the recursion. If the subarray of interest has exactly one element, then end would be equal to start plus 1. There is nothing else to do because an array of one element is already sorted, so I simply return. Note also that merge sort does not return any value, so its return type is void. Otherwise, if the subarray of interest has more than one elements, I first find out the mid index in the subarray of interest. So this is simply start plus end over 2, and then I am going to recursively call merge sort twice, once for the subarray of A starting at start ending at mid minus 1, and then for the subarray of A starting from mid and ending at end minus 1. Once these two calls return, I know that these two subarrays, the part of A between start and mid minus 1 and the part of A between mid and end minus 1, are already sorted. After that, I simply need to merge these two sorted subarrays to get the entire sorted array A. So that is accomplished by calling this function merge sorted subarrays, which takes the array A, and the two subarrays in there, the two sorted subarrays in there are from A start through A mid minus 1 and A mid through A end minus 1. And finally, since merge sort does not return any value, I simply return from here. So this is the key step in merge sort. How do we merge two sorted subarrays? Let's see how this function might look like. So to merge two sorted subarrays, our precondition is that the two subarrays A start through A mid minus 1 and A mid through A end minus 1 are sorted in decreasing order, and the post condition that we want to guarantee is that the entire subarray from A start through A end minus 1 would be sorted in decreasing order. Now inside merge sorted subarrays, what do? We actually have two counters or running indices, one for the first subarray and the other for the second subarray. So I will be the running index for the first subarray A start through A mid minus 1, and J will be the running index for the second subarray A mid through A n minus 1. I am also going to use an integer array called temp A of the same size as the array A, which is passed as a parameter to this function. In our case, the size was 100, and I am also going to use an integer variable called index, which is initialized to start. This temp A array is basically where the merged and sorted subarray is going to be temporarily stored, and later on we will copy the merged and sorted subarray from this temp A back to A. This integer variable index basically tells us where the next element of the merged and sorted subarray should be stored in the array temp A. So let us see how we might use them in doing this operation of merging sorted subarrays. So here is our central and important merging loop. In this loop, I am going to initialize the running index for the first subarray to start, the running index for the second subarray to mid, and I am going to iterate in this loop as long as there are elements to examine in either of these two subarrays. So as long as either I is less than mid or j is less than n, I am going to iterate in this loop. Note, I have not incremented the values of I and j over here in the for loop. These will be incremented appropriately within the body of the for loop. Now what do I do within the body of the for loop? I have to determine whether ai coming from the first subarray A start through A mid minus 1 or aj coming from the second subarray A mid through A n minus 1. I have to determine which of these two should appear next in the sorted order, and I have to update temp A index accordingly. And if I have basically copied ai to temp A index, I have to increment I. If I have copied aj to temp A index, I have to increment j. And of course then I must increment index, so that the next time around the next element to appear in the sorted order would be stored in the next position in temp A. Now if I take a closer look at the merging loop, then there are two cases to consider in the merging loop. First is when none of the two sorted subarrays have been fully seen yet. Basically both I is less than mid as well as j is less than end, and the other case is when one of the two subarrays is already fully seen. Now this is the easier case, when one of the two subarrays is already fully seen. What do we do then? We simply copy elements from the other subarray to temp A. How do we implement this in C++? Here is a simple piece of code to do that. Basically we check if I is less than mid, then certainly the subarray from A start through A mid minus 1 has not been fully seen yet, but since I am in this else part, and therefore it cannot be the case that both the subarrays have not been fully seen, therefore it must be the case that one of the subarrays has been fully seen, but since I is less than mid, it must be the case that the other subarray, the second subarray, the subarray from A mid through A n minus 1 is fully seen. So in this case, I will simply copy ai to temp A index and increment I. The other case is when I have fully seen the first subarray A star through A mid minus 1, and therefore I am simply going to copy elements from the second subarray to temp A. So Aj will be copied to temp A index and J will be incremented. What do we do when none of the two subarrays have been fully seen yet? We have to find out which of Ai coming from the subarray A star through A mid minus 1 or Aj coming from the subarray A mid through A n minus 1, which of these two Ai or Aj should be the next sorted element, and I must copy that element to temp A index and I must increment I or j appropriately. So this is how we do it. We basically check if Aj is greater than Ai. If so, then I am going to copy Aj into temp A index. Recall that we are trying to sort the array in decreasing order. So whichever one is greater, I will copy that into temp A at the current position index. And because I have copied Aj to temp A index, I must increment j. Similarly, if Aj is not greater than Ai, then I will copy Ai to temp A index and I will increment I. So overall, this is the whole story of the merging loop, and if you think back about it, it is actually not a very complicated piece of code, but it is doing something remarkable. It is taking two sorted subarrays, each of size roughly n by 2, and it is generating one merged and sorted array of size n by passing over each of these sorted subarrays exactly once. As you would notice that I is only incremented, j is only incremented, and which means that I am basically going over each of the sorted subarrays only once from its starting index to its last index. After we have merged the two sorted subarrays, we then need to copy the values from temp A to A at all the indices from start through n minus 1. So this is done by a simple for loop over here, where I have reused the running index for the first subarray here to denote the index which I am copying from temp A to A, the index the value at which position I am copying from temp A to A. So if you now think back about the basic steps that we required in merge sorted subarrays, this is the key function. We were basically required to read two array elements, compare them, write one of these elements in temp A and also increment the indices. So I can think of this as one basic step, and I also required to copy an element from temp A to A when I was copying the entire array from temp A back to A. So let us count how many basic steps would merge sorted subarrays require if I started off with two sorted subarrays, each of size n by 2. Well, since I am iterating over each of these sorted subarrays in a single pass, so at most n by 2 basic steps would be required to iterate over each one of them. This basically means that at most n by 2 plus n by 2 or n basic steps are required to get the merged sorted subarray in temp A. And finally, of course, I have to copy temp A back to A, so n basic steps are required over there. So overall, at most 2n basic steps are required if I feed two sorted subarrays, each of size n by 2, to merge sorted subarrays. Now how many basic steps would the whole of merge sort require? Let Tn denote the maximum count of basic steps to sort an array of size n by merge sort. If you look at how merge sort operates, it basically recursively calls itself twice with half the array sizes, and then it merges the two sorted subarrays. So Tn should be equal to Tn over 2 to account for the first recursive call of merge sort, plus another Tn over 2 to account for the second recursive call of merge sort, and then plus 2n, which is to account for the call to merge sorted subarrays. And of course, the termination case here is T1. When I have an array of size 1, I need exactly one basic step. And if you go ahead and solve this recurrence relation using standard techniques, you will find that Tn is roughly the ceiling of 2n log n base 2 plus n. Now compare the number of basic steps required in merge sort with that required in selection sort. So I have sort of plotted it here for different values of array sizes from 10 through 100. The blue bars show how the number of basic steps increase in selection sort. The orange bars show how they increase for merge sort. Clearly merge sort is a winner here compared to selection sort. So merge sort is expected to be much faster than selection sort for large n. So in summary, we looked at a C++ implementation of merge sort using recursion. We analyzed its performance by counting the number of basic steps required to sort an array of size n, and clearly merge sort wins over selection sort for large n. Thank you.